Hello, physics class. I'm about to continue our discussion about machines and mechanical advantage. Right now, on the calculation side of things and figuring out things about 6 simple machines, but we are going to see what we can do about doing our best to practical objects at home as we progress through the week. So do please put it on your calendar to meet together with Zoom on so that we can do some things, have some discussion. Tomorrow there'll be a good playlist for you. There's going to be an editable playlist. We're going to get into some of the fun stuff behind the simple machines. So I'm trying to make that fun for you anyway, even though I'm looking forward to sharing the experience with you in one way, shape, or form. But it all starts with the 6 simple machines that are listed here. We have a lever, we have a wedge, pulley, inclined plane, wheel and axle, and screw, and we need to talk about each one of them and what they actually mean. A lever is an interesting thing. A lever actually has the one that I'm going to show you, but there are other types of levers as well, and briefly mention those. There's actually 3 classes of lever, but we're going to just take a look at the simplest one first. And in the simplest type of a lever, you've got some kind of a fulcrum, and what happens is you push on one end and the other end changes or pushes the other direction. This would be like in a saw or anything that you would stick a crowbar under to try and move it. You push on one side and then the other side would end up going up or down, as it were. So if you push down, the other side goes up because there's this thing in the middle called a fulcrum. So if you're pushing on this side, that's your effort force. And then what happens on this side as a result is the resistance force, which is going against the resistance of whatever it is that you're trying to move over here. So you've got the effort going in on one side, and it moves this side of the lever in a certain direction. So that is the effort distance. Over here you have the resistance distance, which is how far the other side of the lever moves. So what happens in this case is because the fulcrum is closer over here, you push here, you're pushing for a longer distance. Over here we get a shorter distance, which means that the force that's able to come out of this to move something is greater on the other side. So that's kind of one of the advantages to having a lever like that, especially that type of a lever. Okay, and there are other levers as well. For example, a baseball bat is a good example of a lever, but in that case, the fulcrum is where the hand, your closer hand is, the hand that's like right at your closest to you, and then you're putting the force in, for the most part, with your outer hand. If you're a right-handed batter, you're pushing in the force with your right hand. If you're a left-handed batter, you're putting in the force with your left hand. So the fulcrum is your non-dominant hand, and you push that in, and so then what ends up happening is that the resistance is the part that hits the ball, so it's configured a little bit differently. And another example of a lever is like a wheelbarrow, where you're trying to lift something up and you're pulling up. The fulcrum is at the far opposite end. Okay, so the fulcrum will be down like here, and you'd be like pulling here. The other fulcrum would be here, and then the load or the resistance would be in the middle. So there's several different things for a lever that your book doesn't go into. Your book just hits this one, but I wanted you to be aware that there are 3 classes of levers, and they're used for different purposes. We also are looking at the simplistic view of a pulley. All right, in this case, a pulley just wraps around something and you pull down on one side and the other side moves up. Or you pull, the pulley is maybe sideways way, and the result is that it changes the direction of force. And that's a simple, what we call a fixed pulley, because the pulley's there and something's wrapped around it. But there are other types of pulleys that actually are designed to move, in which case more things are going on, but we're looking at the simplest case of these simple machines. So in this case, you've got the effort force pulling down, the resistance force pulling up. The effort distance is how far it moves this way. The resistance distance is how far it moves this way. These really should be fairly close to equal, because it's really just changing the direction of force. Probably you'd have a little less force coming out than going in, because there's probably just a little bit of friction on here. It's really impossible to have a frictionless pulley and to get all of that work to transfer over. Another type is called an inclined plane. An inclined plane would be something like a wheelchair ramp or something like that. So you would be pushing the thing along this way. So you'd be making your effort force in this direction. But the result, and this is the surprising part, the result is that whatever it was didn't have to go straight up. So the result, or the resistance, is this straight up motion from here to here. It's kind of a different type of machine. A lot of times people wouldn't even think of it as being a machine, but it is one. So your resistance distance is this way and your effort distance is this way, going all the way along here. So that effort distance, you traded that long distance with a little force so that you could multiply the force, but you're really only going just a small distance upward. So it's an interesting thing where you're trading long distance so that you can apply less force, but it does work out very well that way, and it does fall into the machine category. A wedge is useful for being able to split wood, or it's used in a zipper, or in various other different ways. It is a movable inclined plane. So instead of the thing being pushed up the ramp is really actually being shoved through whatever it is that's being split. So this wedge type of a thing, you might be pushing down on the wedge, and what it's doing is it's splitting back and forth. Now I want you to hold in your mind that when you use a pair of scissors, it's really a wedge that's pushing through the paper and splitting it. When you're cutting up kind of meat or bread or whatever it is that you're cutting, you're using a wedge to do that cutting, or a pair of scissors. If you look at them, there's a little edge that's its own type of wedge that's splitting. Now what happens is the effort force is this way, which would mean that the distance would be this way. So you're pushing this down this way, and what it does is it changes the direction of the force to be going out this way, and it might be going just a smaller distance so that it can magnify the force. It splits it in two different directions, and it can also change the direction of the force, which is very, very helpful. So this would be a wedge in how it works. Another one's a screw. Now I have a screw drawn here. Now the effort, it's kind of hard to see. It's kind of coming off at a tangent. So you've got a screwdriver and you're turning that screw. And what happens is the effort's going kind of like around the screw as it goes, but the resistance, or the result, is that it's pushing in this way. This works also with something called a C-clamp. I'm going to try to find some kind of a video or something to show you what that looks like. I don't have access to my closet of wonders where I have that I could show you easily, but a screw where you've got something that's turning, and what it does is it's really just kind of like it's kind of like an inclined plane that's wrapped around a cylinder, is what that is. It's an inclined plane wrapped around a cylinder. So the result is force this way after you've applied force this way, and round and round and round, as far as how that goes. All right. So the effort distance would also be this way, and the resistance distance would be this way. I do want you to draw these things and write them down. There is something, when you take your test on this, it's to get the different pieces of it turned in and graded, and I am still working on that out in my head, how that's going to work. All right, a wheel and axle. Okay, a wheel and axle usually is used in the context of possibly like some kind of a hand crank. Okay, so if you're turning a hand crank, what I have, I don't know if any of you have ever played the game of Mousetrap. I do have that at school, and if we, whenever chance to see each other again, I hope to play a game of Mousetrap and show you the wheel and axle right up close like that. But if you've ever seen, like when you are trying to go to a wishing well or something, if you turn the crank on the outside and then that rope wraps around the inside and pulls up the bucket of water, you would have that. So you would have the effort being around the outside. Now the effort doesn't have to be like a rope or anything pulling down. It can be actually a handle that you're turning around and around on the outside, and then there's a little axle inside where it is spinning and causing the resistance to go the other direction. So it's kind of like a pulley with attitude, because you've got a bigger circle that's going around so that you've got this force, and then it's translating to this smaller distance, which allows that force to do a different type of a job. So hopefully you've drawn in your diagrams so that you have them and you have them to refer to. Now we know that a lot of times you don't have one machine, you have a whole series of machines that work in tandem with each other. They're connected so that the effort from one turns into a resistance, but then that becomes the effort for the next machine. And when that happens, we call it a compound machine, because it's not just one part, it's a piece that's making another piece happen, that's going to make another piece happen, that's going to make another piece happen. And what we're going to do is we're going to take a look tomorrow at some, they call them Rube Goldberg machines. The Rube Goldberg machines are machines make up usually for fun, where you take something, a simple task, and you make a complicated machine to accomplish that task. And so we're going to do that. We're going to see what you can design at home. This is the interesting thing, is every year, few years, people brought stuff in and were able to show what they created in live and in person. And I know that people can't get out to shop, so this is going to be an interesting exercise in creativity and figuring stuff out. I know that sometimes at the beginning of the project in normal years, when a compound machine has to be built, people are like, oh, I don't know what to do, I don't know what to do. But we're going to look at a series of videos and let your creative juices get flowing and see what kind of fun to do that in the context of your room, because you can be free to build it a little bit longer and keep it going a little bit more, and the purpose to this is to have a little bit of fun with it. So I'm hoping that through scrounging around and a little creativity, you're going to be able to accomplish some very, very interesting things for us to share, and happen as we get a little bit more towards this project. But today I said our focus was going to be mostly on calculations, so I have a couple of problems for you to take a look at. The first one is dealing with a wedge, and it's used to split a log. The wedge is driven 0.3 meters into the log. If you think about that picture we just had, the log is separated 4 centimeters. So in other words, the distance that goes side to side would be a 4 centimeters separation. There's a force amount that's needed to split the log. Those wood fibers are going to hold on very tightly, and the wedge is being pushed. In other words, the effort that you're making is this much force being pushed. So what we need to do is we're going to use some of our calculations in order to find other information. We want to find the ideal mechanical advantage. In other words, what would happen if this were a perfect machine? We're going to find the actual mechanical advantage based on this information, and then we're going to calculate the efficiency of this particular device using some of those equations we talked about yesterday. So the ideal mechanical advantage is dE over dr. Now, in order to do this problem, we have to go through and we have to identify the different pieces. dE is the effort distance. That's the distance that you put in order to do this particular problem. Now, we have two distances. We have the 0.3 meters and we have the 4 centimeters. Okay, so the effort, the part that you are putting in, and then the resistance is the result of what happens because of that. So the wedge is being driven in 0.3 meters. That's what you do. Okay, so since that's what you do, this part right here, this is your effort. The resistance, that what happens as a result, is this 4 centimeters. That's the result. That's what happens because of what you do. So we do have to have the same units, so you do need to think it through a little bit, that 4 centimeters is 0.04 meters. We have our 0.3 meters that was given, our effort, what we did, and the resistance, or I think of the R as result because it helps me to think better. The result is that it went in 0.04 meters, so the ideal mechanical advantage would be 7.5 for this. Meaning that you would have 7.5 no units. That would be the ideal if it were perfect. Our actual mechanical advantage, though, is FR over FE. So our resistance force, or the force that we use, divided by the effort. So we need to nail down which one's which. So in other words, we need to figure out which parts are effort and which parts are resistance. So I want to think about what part is my effort in this. This is how much is needed to split the log, so that would be what's the result that's needed, but you pushed with this force. So this part is your effort. The part that happened because of the force that you applied is this right here, which is the resistance or the result. So we'll put those numbers in here. 2.3 is the result, 2.3 times 10 to the fourth. 1.2 times 10 to the fourth is the actual effort that you put in. So our actual mechanical advantage for this particular device is 1.92. So this would be our ideal, and this is what really happened. Okay, it's kind of like a nailed it thing. This would be perfect, but this is what actually happened. Okay, so when we look at how efficient that is, we're comparing the mechanical advantage to the ideal mechanical advantage and making it into a percent. So in other words, moving the decimal over 2 places, which is where the times 100 comes in. So what we need to do, mechanical advantage we said was 1.92, and that's what really happened. The ideal would be 7.5. So what we find out that this wedge is only 25.6% efficient as far as the work in and the work that results because of it. So that's one way of thinking about the efficiency, is the reality compared to what the ideal or what perfect would be if you could get rid of friction. Now, when a log is split, there's a lot going on. There's heat generated. There's all kinds of, there's different things that are happening as this log is being split. So this efficiency is not necessarily bad, but it's just what's happening. Now, if you sharpen your axe a little bit more, you'll become more efficient. So as a knife gets more sharpened, it becomes more efficient, and more of that force in. If you've ever worked with a sharp knife or a dull knife, if you're trying to cut something up with a dull knife, it's not very efficient. The percentage is probably way lower. But when you have a sharp knife that's sharpened, then the efficiency would go up and the percentage would go up. So let's look at one more for the day. You exert the force of 380 newtons on a lever to raise a rock. So sometimes people will do that when they are gardening or whatnot. You use a simple lever. A hoe is actually an example of a lever, or a shovel, and you're trying to move this rock or this tree root. I know I've been there, done that, where you've actually used a shovel or some other thing as a lever to try and move something. We have this rock, and it's a 2,500 Newton rock, and it needs to be it's going to be lifted a distance of 5 centimeters. They give us the efficiency of the lever, and they're trying to ask how far did you move your end of the lever if you exert that. So what we need to do is we need to identify the pieces and parts we have in terms of the resistance distance, the resistance force, the effort distance, and the effort force. So here we have, you exert the force, that's our effort force. And the result, oops, I did not mean to do that, sorry. The result is that you have 2,500 newtons rock got moved. You move it a distance of 5 centimeters, that's a result. Notice that I changed it into its decimal form for that. 79.2%, well, that's my effort percent. Remember in our original formula you had that times 100? Well, the only way to get rid of that times 100, just make your percent into a decimal, and then you don't have to deal with that times 100 anymore. So 0.792 is a decimal version of 79.2%. So one of our effort equations deals with the work out compared to the work in. We now have a force times a distance and a force times an unknown distance because it's asking you how far. So our output would be the R's, FR times DR, FR times DR, and our input would be FE times DE. And so we would have this problem to solve. So we dust off the old algebra skills. I'm going to multiply both sides by 380 DE so that these will cancel out, and I'm moving my DE up to the top. Doing a little bit of calculations here. Sorry about that. Where that becomes 300.96 when I do 380 times 0.792 times DE equals 125. Divide that by your 300.96, and we get that our effort distance was 0.42 meters. Think about that in context. A doorknob is probably about 1 meter high. So 0.42 meters is approaching half of that. So that would be the distance that you'd be moving the end of that lever or the end of that shovel. All right, so that's about all I've got for you today. Have a good rest of your day, and we will look forward to doing some things with Rube Goldberg machines.